Assalamu alaikum. In this lecture, we are going to start with the new topic, and the new topic is flexible pavement design for airports. And we are going to use FAA method for the design of flexible pavements. FAA is the abbreviation for Federal Aviation Administration. Okay, before I start this topic, let's look at the difference between highway pavement and the airport pavement. So there are some basic differences between highway and airport pavement. So one difference is in highway we always use 18 kip standard axle. So we convert all the loads in form of 18 kip standard axle, and that we call equivalent standard axle load, ESAL. So there is nothing axle load something. There is no axle load in airports. So for airport pavement, because the aeroplanes are going to use this airport, or aircrafts are going to use, there is no axle in aircrafts. Rather, we use gear, and the equivalent of standard axle is the design aircraft. We will talk about what is design aircraft and how to find this design aircraft. Okay, as I was telling you, in highways we have axle load. There is no axle in aircraft, so we use here what we call it gear. So there are landing gears. So there are two types of landing gears. One is called there is a gear at front, we call it nose gear, and then the other one is called the main landing gear, main gear. So these configurations are called gear. Okay, there's one more difference, is that we convert all the load in highway in terms of equivalent standard axle, or we call it W18. Okay, in case of airport pavement for aircraft, we are going to convert all the traffic in terms of design aircraft, and we call it annual departures of design aircraft. Annual departure of design aircraft. This is also called equivalent departure. Okay, in case of highway, the maximum load acts on the design lane, and this design lane is always the outer lane. These are mostly the truck lanes that receive the heaviest load. So the design lane is always outer lane, and this design lane takes the heavy load. So heavy load, the maximum load is always on the outer lane. In case of airport, the heavy load is going to be in the center of the pavement. So the heavy load is in the center of pavement. So these are some of the differences. So we can summarize. There are 1, 2, 3, and 4. These are the 4 major differences in the pavements of highways and airport. Okay, let's start. So when we design our pavements, we always consider the takeoff weight of the aircraft, the maximum anticipated takeoff weight. Okay, the reason we use takeoff weight, because when aircraft is going to take off, its weight is more because it is full of fuel. That's why we always use the takeoff weight. And normal the procedure is we consider that 95% of the load is taken by the main gear, and only 5% of the load is taken by nose gear. Let me show you the picture of this typical aircraft. So here, this is called nose gear. Nose gear, and these are the main gears. So these are the main gears, or you can see also here, these are the main landing gear, we call it landing gear. And if you observe in this figure, there are some red shaded areas. These red shaded areas are the fuel, because aircraft consumes a lot of fuel. That's why these are the places where the fuel is stored. Mostly the fuel is stored in the wings and in the main body. Why it is stored in the wings? Because the engines are also attached with the wings. So here fuel is going to be used is going to be used by the engines. Okay. So anyway, there are two gears. One is called nose gear, and other one is called main landing gear. The landing gear is going to take 95% of the aircraft load, and the nose gear takes only 5%. So this is this convention we are going to follow in our calculations. Okay, so the gears have different configurations. We are going to see in a short while the details, but the landing gears are mostly, these are the types: single gear, dual gear, dual tandem, or wide body aircraft. Okay, the pressure of the aeroplanes is going to vary from 75 to 200 psi. So if you remember, when we design highway pavements, we consider the standard axle, and that standard axle has a pressure of 70 psi. So when we design, we consider 70 psi in standard axle. But in case of airport pavement, these aeroplanes might have pressure ranging from 75 to 200 psi. Okay. About the traffic volume, in case of, if you remember, in case of highways, we always convert all the traffic in terms of standard axle, and we express it as W18. So typical values of W18 are going to be, let's say, 15 million passes. So this is how we find 15 million passes. These are the passes of standard axle in the total design life, and this is the traffic load that we use in highway pavements. But in case of airport pavement, we are going to calculate traffic volume in terms of annual departures. Annual departures means aircraft, how many times is going to visit a typical airport in 1 year, how many times it is going to land on the pavement in 1 year. That is called the annual departure. Okay, so as we know, the configuration is it could be single gear, it could be dual gear, or it could be tandem gear. So in case of single gear, there is one wheel in the front, we call it nose wheel, and there is going to be one wheel on one side and one on the other side. This is either in the body of aircraft, or it could be attached to the wings of the aircraft, depends on the design. So this is single gear configuration. Okay, so if there are two wheels on one side and two wheels on the other side, this is called dual gear configuration. And if there are four wheels like this is called dual tandem. Okay, these are some of configurations. Okay, so let's look at the typical aircraft weights. So here in this table, if we see, there are different plane types these are their commercial names. For example, here all of these are Boeing aircrafts. Boeing is an American company that manufactures passenger aircrafts. And then there are some other companies here, for example, this Lockheed, McDonnell, and others. So the weight, this is the maximum takeoff weight of this aircraft, and the gear type is given here. Okay, and some other dimensions, and the pressure. The pressure, if you look at, it goes from 150, minimum is 127, and the maximum we see is 200. So it goes up to 200 psi. Okay, so here is another sketch showing the weights of the aircraft and their size. So at the moment, the heaviest aircraft is Airbus A380. So Airbus A380 has this this weight. It is 1.3 million pounds. This is the heaviest aircraft that is being manufactured these days. Okay, so if we look at the aviation industry, the aircraft weight has increased exponentially. So in the beginning, the weights were not that high, the aircrafts were not that heavy, but now if you look at this, growth is exponential. So this is a kind of, you can say, it's an exponential growth. Okay, so the heaviest is 1.3 million pounds, which is Airbus A380. So here is a picture of gears. So if you look at, there are 6 wheels on one side, and then there are 6 wheels on the other side, and these 6 wheels are in the body of aircraft. And then there are 4 wheels on one side and 4 wheels on the other side. They are in the wings. So altogether they are 20 wheels. So this is a typical aircraft. So here is a landing gear of Boeing 777. So there are 6 wheels. This is called landing gear. So let's look at how these wheels are pronounced. So if there is one wheel, we call it single. This configuration is called single. If there are 2, we call it dual, D. If there are 3 in one row, we call it triple, T. And if there are 4 wheels in one row, we call it quadruple, Q. So S, D, T, and Q. Okay, these are the basic naming convention. Okay, if there are 2 single wheels, we call it 2S. If there are 3 single wheels, they are called 3S. So if there is one row of dual, it is one row of 2 wheel, it is called dual. And if there are 2 rows, this is called 2D. Similarly, if there are 3 in one row, it's called triple, and if there are 2 rows, this is called 2D. So 2T. So most of the time we will find this 2D or 2T. These are most common, or maybe this one also. So these are the common three types we are going to encounter in our problems. Okay, here are some of the typical configurations. So if it is a single wheel, then there is one wheel on one side of the body and on the other side. Okay, in case of dual, there are 2 wheels on one side, 2 wheels on the other. If it is dual tandem, this configuration is actually 2D. So there are 4 wheels on one side and 4 on the other side. And this is a configuration for Boeing 777. This is DC-10, and this is Airbus 340. Okay, there are some other configurations. This is the heaviest aircraft of the Boeing series, and this is the heaviest aircraft of Airbus 380. So if you look at Airbus 380 has 20 wheels, and the Boeing 747 has 16 wheels. Okay, now let's talk about the design aircraft. Now, in case of as we summarized in the beginning, in case of highway pavements, we always convert all the axle loads in terms of standard axle, and the standard axle is always 18 kips. So we convert all the traffic in terms of 18 kips standard axle load, and that is called W18, or this is also called ESA. But in case of airport pavement, we are going to find out the design aircraft. Now, at a certain airport, there might be different aircrafts landing on the pavement. So the aircraft that needs the maximum thickness is called the design aircraft. It means if there are a number of aircrafts coming on the airport and they are landing on the pavement, the aircraft that is going to require the maximum thickness is going to be called as the design aircraft. It is the aircraft that is going to produce heaviest single wheel load. So how to find out the design aircraft and how to convert the traffic in terms of design aircraft? For that, we are going to follow this formula. So here, this is the annual departures of any aircraft. So this is there are a number of aircrafts coming on the airport. So this is suppose aircraft I could be 1, 2, 3, 4, any number, and this is the conversion factor for the aircraft. Okay, WI is the single wheel load of aircraft I, aircraft that is under consideration, and this is the single wheel load of design aircraft. And this is the heaviest. So if we have a number of WI values, so the heaviest one is going to be W. So we are going to use this relationship to find out the equivalent departure. So this is called equivalent departure in terms of design aircraft. So these are the equivalent departures. Okay, so Fi is a conversion factor, and for the conversion factor we are going to use this table. So we will see when we do the example how to use it. Okay, let's now do one example to understand how to use these relationships. Okay, here is the example data. We have a number of aircrafts, and from some certain survey we got this data. For example, that these are the possible aircraft which are going to visit the airport, and for that airport we have to design the pavement, and there are 1, 2, 3, 4, 5, 6 different type of aircrafts. So their aircraft name and its gross weight is written in this first column. So for example, the first one is Boeing 727, the second one is Boeing 727-200. This is a different model. 100 is different model, 200 is different. Then Boeing 707-320B, DC-930, CV-880, and then we have Boeing 737-200. Their gross weights are written in the parentheses. The gear type are written in the second column. The annual departures, these are the estimates that this type of aircraft is going to land in 1 year 3,500 times on this airport. So these are the annual departures for each aircraft. Okay, so this is the data which is given to us. These are the 3 columns which are given to us, and from there we have to calculate we have to determine what is the design aircraft. So what is the design aircraft? So for this design aircraft we need what is the weight, total weight. what is the gross load or gross weight, what is the gear type of this aircraft, and the third thing is what are the equivalent departures in terms of this aircraft. So we have to find out these three things. Okay, let's start. Okay, the first step is to find out the wheel load or the load which is acting on each wheel. So if we look at the dual means, there are going to be two wheels on each side. So the total wheels are going to be 4. So in case of dual gear, the total number of wheels in landing gear are going to be 4. 2 on one side, 2 on the other side. So this is 2 and 2, 4. Okay, dual tandem is actually 2D. It means there are 4 wheels on one side and there are 4 wheels on the other side. So this there are total are going to be 8 wheels. So I'm writing here number of wheels. So 4, then 8, and then there are 4. And we know that the main landing gear takes 95% of the load, and from that concept we can find out what is the weight on one wheel. So let's look at the first row. It is 160,000 pounds. So the wheel load is going to be, the single wheel load is going to be 160,000, and it takes 95% of the load, means 0.95, and number of wheels are 4. So if we multiply 160,000 0.95 divided by 4, so it comes as 38,000. So one wheel is going to carry 38,000 pounds. 38,000. So this is 38,000. So I'm not going to write units because I have written here the unit is pound. Okay, next. Okay, 190,500, again 4 wheels. So if we multiply 190,500 with 0.95 and we divide with 4, we should be getting 45 to 44. Okay, there are some decimals I'm ignoring because these numbers are big, so we can ignore those decimals. Okay, so the third one is going to be 38,831. Okay, the fourth one, if we calculate, it should be 25,650. Next is 21,909, and the last one is 27,431. So if we look at this column, the heaviest wheel load is in this second case. So this is actually the heaviest load. So this is our design aircraft. So it means the design aircraft is Boeing 727. Okay, this is not important. Important is what is the gross weight, what is the gear type. So I can write here that our design aircraft, I can summarize here, is the for design aircraft, the gross weight is 190,500 pounds, and the gear type is dual, and the last thing is the R equivalent. This is what we have to now focus on. Okay, the next thing is to calculate this conversion factor, Fi. So what we are going to do is we are going to convert the gear type, because the gear type of the design aircraft is dual. So we should convert from dual to whatever is the, for example, if you look at the first row, the gear type is dual, and we have to convert from dual to dual. So the dual to dual, there is no conversion, means the conversion factor is going to be 1. Okay. If it is dual to dual, definitely conversion factor is 1. Now we have to convert from dual tandem to dual. So we have to go from dual tandem to what is the design aircraft. Design aircraft is dual. So we have to convert from dual tandem to dual. So this one was dual to dual. no conversion, means 1. This is dual to dual, and this conversion is from dual tandem to dual. So dual tandem to dual, we are going to look at the table. Okay, do we have the table here? Okay, let me bring the table. Okay, here is the table, and we have to convert from dual tandem to dual. So this is dual tandem, and we have to go from dual tandem to dual. So when we want to go from dual tandem to dual, the conversion factor is 1.7, and you will see here you will not find any conversion from dual to dual, and similarly you are not going to see the conversion from single to single. You are also not going to find the conversion from dual tandem to dual tandem, because all of these conversions are 1. This is common sense. So that's why they are not mentioned here in this table. So anyway, from dual tandem to dual, this conversion is 1.7. So let's go back to our table and put it here. From dual tandem to dual, it should be 1.7. Dual to dual is 1. Dual tandem to dual is 1.7, and this is also 1. Okay, so the next step is to calculate this log R equivalent. Okay, so here is the formula to calculate R equivalent. So in this formula, Ri is the annual departures of the aircraft that we are considering. Fi is its conversion factor. Wi is the wheel load of the aircraft that we are considering, and this W is actually the wheel load of design aircraft. This is related to the design aircraft. Okay, this is actually the heaviest load. So if you look at this column, so this is the heaviest value in this column. So this heaviest value was 45,244 pounds. Okay, so let's put the values. Ri is 3,500, and if we put the values and solve, we should get 3.2480, and when we take the inverse log, it will be 1770. So I'm not using any decimal, I'm rounding off to full digit. So this first value is going to be 1770, and let's calculate the other column. So the other values are going to be, okay, I have calculated all other values in this column. So we have got all the R equivalent values. Now let's add them. So when we sum all these values in this last column, we are going to get, this is the total R equivalent. So now our information is complete. So here is the summary. The design aircraft is dual gear. The total gross weight is 190,500 pounds, and when we convert all the traffic in terms of this design aircraft, the equivalent departures are 15,510. So this information is going to be used as input when we design the pavement structure. Okay. Now let's talk about the typical cross sections and the plans of the pavement, highway pavement or runway pavement. So let's look at the typical sketch. So here is the sketch for flexible pavement. So this is the center. You can call this is the center line of pavement, and there is a transverse slope on both sides. We call this camber. This camber is provided to remove any rainwater, so that rainwater should not accumulate on the surface. Okay, so this we have 3 layers. So this first one is asphalt concrete. The second one is this is base, and the third is sub base. The typical pavement is 150 foot wide. So from the center on both sides, 25 foot thick, we give the total thickness, what we call it critical thickness, the thickness that we are going to calculate shortly. So this thickness is called T. So whether it is, I'm just writing here T, but this could be D1. So for example, if this is D1, the thickness of asphalt concrete, D2, which is the thickness of base, and D3, which is the thickness of subbase. So this in first 50 foot, 25 foot on each side of the center line, we provide the total thickness, the thickness that we are going to calculate. We call it critical thickness. Then this thickness is going to be reduced in next 25 foot. If this thickness is, for example, if this thickness is D1, so here it will become 0.7 D1. It reduces to 70%. If this thickness is D2, this will reduce to 0.7 D2. So up to 25 foot thickness remains same, and after that it tapers from 100% thickness to 70% thickness, and after that it remains same. So this remains 70% of D1 and this remains 70% of D2. So what happens with the D3? Yes, that thickness is going to increase because the total thickness has to remain same. So why we do that? Because the heavy load is always in the center. So the center portion is going to take the full load. That's why this is called the critical portion. So this critical portion is the center 50 foot. This is 50 foot where we provide full thickness, and after that this thickness is reduced. So this is tapered from 100% to 70%. So here we reduce from 100% to 70%. 100% to 70%. So this is a typical thickness of a pavement. And remember, the airport pavement or runway is always 150 foot. And if we need to design a pavement which is more than 150 foot, then we are going to increase here this thickness. So for runways which are wider than 150 foot, this dimension has to increase on both sides. This dimension is going to increase, and this you can call it as shoulder. This is to increase the lateral stiffness. So these are shoulders. So this is a typical cross section of the runway. Okay, let's go back. Okay, let's move on. Now we will talk about the pavement design proposed by FAA, Federal Aviation Administration. This method is also called CBR method because the design is based on CBR values. We know what is CBR. We have studied it before. CBR is California Bearing Ratio. So in this method, we take the minimum CBR for base as 80. So this is the minimum. So if any material whose CBR value is less than 80, that cannot be used for base. So this is the requirement. Okay, and the minimum requirement for sub base is 20. So any material whose CBR value is above 20 or above, it can be used as sub-base material, and if CBR value is more than 80, then it can be used as the base material. Okay, so there are different type of base materials there which have been given in this method, and similarly there are different type of sub-base materials. It could be crushed aggregate, it could be aggregate which is stabilized by limestone, cement, or any other thing. Okay, so the important thing is here to remember that for base course the minimum CBR is 80, and for sub base the minimum CBR is 20. Okay, there are some requirements by this method. The requirements for the compaction of subgrade. So this table summarizes the requirements of subgrade compaction for both cohesionless soils and cohesive soils. For cohesionless soils and cohesive soils, and for different gear types, and for different gross weight of the aircraft. Okay, This is related to construction. Okay, the this FAA method, this Federal Aviation method, Federal Aviation Administration method, they have developed design charts. This is one typical design chart, and this is the design chart for single wheel gear. Similarly, there we will find a chart for dual gear. If our design aircraft is dual gear, we are going to use this chart. If our design aircraft is dual tandem, then we are going to use this design chart. And these are the charts for certain type of models, aircraft models like Boeing 747, and there are different variants of 747: 100, SR, 200B, 200C, 200F. Anyway, and here is Boeing 747 SP is a different model. Okay, there are another design charts for different manufacturers. This is DC-1010 and DC-10CF. Okay, the next thing is the minimum base course thickness requirement. For minimum base course thickness requirement, we can use this table, but I prefer to use this design chart. This is the design chart for minimum base course thickness. So let's do one example, and from here we are going to learn how to use these design charts. Let's move on to our example. Okay, let's do this problem. A flexible airport pavement has to be designed for the given data. The design aircraft is a dual gear aircraft, and the gross weight of this aircraft is 70,000 pounds. The annual departures of this design aircraft, what we call that, and we call this equivalent departures, are 6,000. The CBR value of subbase is 20, and the CBR value of subgrade is 6. Now, because the design aircraft is dual gear, it's a dual gear aircraft, so we are going to pick the appropriate design chart. So this is the design chart for dual gear aircraft. Okay, so if we look on this design chart, there is some information there on top. It says that these curves are based on 20 years design life, and the critical thickness of the top layer, which is the bituminous layer or asphalt layer, is 4 inch. So from here we get this idea that D1 is going to be 4 inches. Okay, next, if you focus on this graph, there are some lines which are going down with the negative slope. These are the aircraft weight, gross weight. So if you look at, the weights are so 50,000, 75,000, 100,000, 150, and 200,000. So our aircraft in this problem is 75,000. So we are going to use this line. Okay, next, the annual departures. So annual departures or equivalent departures of this aircraft is 6,000. So if you focus here, and I have zoomed in this part of the graph, so there are 5 lines. The first this line, a curve, is for 1,200 departures. Second line is for 3,000 departures. Third line is for 6,000. Fourth, 15,000, and the last one is 25,000. So in this problem, the annual departures are 6,000. So we are going to use this third line. Okay. So first thing is if I sketch this problem, there are 3 layers because it's a flexible pavement. So the first one is this asphalt concrete, then there is a base, and then there is sub-base layer. So this layer is D1, thickness is D1, base has thickness of D2, and sub-base has thickness of D3, and then is this subgrade, or this is the foundation soil. Now subgrade CBR, the subgrade CBR is California bearing ratio is 6. So when we use this CBR of 6, Okay, we are going to get the total thickness of pavement structure. And if you look at, we also have a value of 20. So when we are going to use this CBR of 20 for subbase, it will give us the thickness of base and asphalt concretes. So first, let's take a value of 6. So if you focus on this design chart, the top row here is CBR values. So our value is 6. So from here, we are going to draw a vertical line up to the weight of the aircraft. The weight of aircraft is 75,000. From there, we are going to draw a horizontal line. So if we zoom in, so this is both the lines are crossing here at 75,000. Okay, and then we stop when we reach at the line of annual departure, which is 6,000. This is the third line, and from there we go down. So I can say that there are 3 lines. The sequence is, this is first line, this is second line, and this is our third line. So in the bottom we get the thickness. This will be total thickness. So when we are going to use CBR equal to 6, this will give us total thickness D1 plus D2 plus D3. So if we zoom in and see, so this thickness should be, so I have drawn these red lines. So 20, 22, 21, 22, 23. It's not 23 exactly, it is 22.9 something, but I'm going to assume it is 23. So this is 23 inches. Similarly, we are going to use the CBR value of subbase. So when we are going to use CBR of 20, and this is, remember, for subbase, what we are going to get is the thickness T1 plus T2. So let's repeat this process. So 20, this is 20. So from here we draw a vertical line, and then we reach up to the weight of the aircraft. This is the weight of aircraft, and from there we draw a horizontal line, and we stop at annual departure of 6,000, and then we draw again a vertical line. Let me zoom in. So this is 9.2 because there are 5 lines. So the least count is 0.2. So this is going to be 9.2 inches. Okay, now we also have to look at the minimum base thickness. For minimum base thickness, we are going to follow this graph. We know that the total thickness D1 plus D2 plus D3 is 23 inches. Okay, D1 is 4 inches, and D1 plus D2 is 9.2 inches. Okay, let's draw a line, horizontal line from the total thickness. Our total thickness is 23. So this is total thickness. This is 23 inches. From here we draw a horizontal line, and we are going to intersect this inclined line where the CBR value is 6. So this is the subgrade CBR. CBR of subgrade is 6, and from there we are going to draw a vertical line, and that gives us the minimum base course thickness. So let's zoom it. So this is close to 7. It's not exactly 7. It is 6.8 something, but I'm going to assume it's 7. So D2 minimum is 7 inches. Means if our calculated value of D2 or base thickness is less than 7, we are going to assume, we are going to take this value as 7. So let me call this as equation 1, and this equation 2. So let's put D1 in equation 2. So put D1 into 2, it should be 4 plus d2 is 9.2. So from here we will get d2 is equal to 5.2. Yes, this 5.2 is less than d2 minimum. Since it is less than d2 minimum, we are going to use d2 is equal to 7 inches. So d2 is 7 inches, d1 is 4 inches. Okay, so let's put d1 and d2 in equation 1. So if we put d1 and d2 into equation 1, we should get d3. So this d3 is going to be 12 inches. So this is our solution. So let me summarize here. This is 4 inches, 7 inches and 12 inches. So the total thickness is 23 inches. Remember, these are critical thicknesses. These are critical thicknesses. So all of these are critical thickness values. So from here we can sketch the cross section, and then we can find out the non-critical thickness value. So this is the procedure for getting the pavement structure values, the thickness of pavement structure for any flexible pavement. Thank you so much. Have a nice day.